The clock is ticking. Less than 3 minutes have passed since the Big Bang. The universe is blistering hot, around 1 billion degrees Kelvin, and expanding at an incredible pace. It's in this unimaginable furnace that something extraordinary begins, the creation of matter as we know it. This phase is known as Big Bang nucleosynthesis. It's the era when the first atomic nuclei, hydrogen, helium, and tiny traces of lithium, began to form from the subatomic chaos. In these scorching early moments, protons and neutrons swirled in an intense plasma, jostling and colliding under unimaginable heat and pressure. Protons, single, positively charged particles, began to combine with neutrons. The very first fusion reactions occurred. The earliest products: deuterium, a heavy form of hydrogen, made from 1 proton and 1 neutron. These deuterium atoms quickly fused again to form helium nuclei, 2 protons and 2 neutrons. A minuscule fraction even went on to create lithium, the third lightest element. But the clock was ticking. This crucial window of nucleosynthesis lasted only about 20 minutes. As the universe continued to expand and cool, the energy levels dropped. Fusion could no longer occur. The opportunity to build new atomic nuclei closed forever. The result of this brief yet explosive period is a chemical signature etched into the cosmos. Roughly 75% hydrogen and 25% helium by mass, with trace amounts of lithium. And this signature remains consistent across the observable universe, across galaxies near and far. It is one of the most powerful and consistent lines of evidence we have for the Big Bang theory. Why is this so important? Because it allows physicists to compare their calculations with what we observe today. And the numbers match. The ratios of hydrogen, helium, and lithium we see in stars and gas clouds reflect the very same chemistry that was written in the universe's first minutes. This alignment between theory and observation is like a cosmic fingerprint, a direct connection to the moment of creation. But the story doesn't stop there. For the next 380,000 years after this initial nucleosynthesis, the universe remained in a hot, dense, and opaque state. The temperature was still too high for atoms to fully form. Electrons were unbound, racing freely through space, and constantly interacting with photons, particles of light. These free electrons scattered photons in all directions. As a result, light couldn't travel far without being absorbed or bounced off another particle. The universe was essentially a glowing fog of plasma, where no light could escape. We call this period the photon epoch, an era of immense light, but no visibility. It's ironic. The early universe was filled with light, but completely opaque to it. The sky would have looked like a brilliant glowing soup, with no structure, no stars, and no space as we know it. So how did we go from that plasma fog to the clear, dark sky filled with galaxies? The answer lies in a coming event called recombination, which we'll explore in the next segment. But for now, let's appreciate just how pivotal these early moments were. In 20 minutes, the universe built the foundational elements of existence. These atoms would later become stars, galaxies, planets, and eventually life itself. All the heavier elements, carbon, oxygen, iron, gold, would come much later, forged in the hearts of stars and violent supernova explosions. But this was the beginning. The first bricks laid in the construction of the cosmos. It's awe-inspiring to consider that every breath you take, every drop of water, every flame, and every cloud carries atoms that were born in this fiery infancy. We are, quite literally, made from the echoes of the first 20 minutes of the universe. And yet, these ancient atoms aren't silent. They continue to whisper their origin through the light they release. That light, some of it still traveling through the universe, gives us a window back in time. Astronomers and physicists use sophisticated telescopes and detectors to measure these signals. They look at abundance ratios, examine absorption lines in distant stars, and analyze the cosmic microwave background, all tools that allow us to peek into those first blinks of cosmic time. Science, in this sense, becomes a form of time travel. We trace particles, we crunch equations, we look deep into the night sky, and all of it brings us back to a moment of pure fire and birth. The early universe was wild, violent, but also finely tuned. If the temperature had dropped too fast, deuterium wouldn't have formed. If it cooled too slowly, fusion might have gone too far, producing heavier elements that would disrupt the balance we see today. Everything, timing, temperature, density, had to be just right. And it was. The Big Bang wasn't just an explosion. It was a precisely orchestrated event, governed by the laws of physics, playing out across a canvas of expanding space-time. And from that event came us.